Hey everybody, welcome back to Calc 3 Online. So the plan for today is start talking about optimization for multivariable functions. And I want to start off just kind of making a connection between last year and what we're going to do today. So last year in Calc 1, right, a local max or min would always occur basically just when the derivative of that function would be 0, right? And those are like your critical points, like the x values where that happen are what they call your critical points. And, if we extend that idea to Calc 3, our notion of the derivative is basically the gradient, right? And so we want the gradient to be really like the 0 vector. So we basically need like f with respect to x to equal f with respect to y, which, so on, however many things we have. I'm just going to do f with respect to n or something. All those need to be set equal to 0, and then we'll solve those out. Like we get like a bunch of different system equations, and that's basically how we will find critical points. So let's do that. So we have this function, okay, and this is where we're going to start to really kind of need to know some things related to like the end of chapter 12, just like identifying what a surface looks like just by looking at the equation. So this one, right, because it's got like z just to the first power and then x squared, y squared, and then you get these two xy terms. Like you could complete the square. But this for sure would be, something of the structure x, like plus or minus a number, and then like plus y plus or minus a number, equals like z. And there might be, some values, some other numbers in there too, but it has like that general structure. And this thing will basically be a paraboloid, and we know it's open up because the x and y squared terms are positive. So, if I just kind of arbitrarily draw one over here or something, this is like roughly what we have. But that, paraboloid is like above the plane down here. So it's kind of sitting up there in space, right? I'm not saying that is necessarily where it is, but it's just something like that. And that's going to be important for finding the local max or min. I mean, we'll know actually already that it should be a min because it has to be like this point down here. So really the question could be worded as find all points where the local min occurs, right? And we'll do it with gradient basically. So f with respect to x is 2x minus 2. F with respect to y is 2x minus 6. So I need 2x minus 2 to equal 0, and I also need that to equal 2x minus 6. So, this would tell me that x needs to equal 1, and this would tell me that, I wrote x, I meant y there. Y minus 6. That part would tell me that y needs to be 3. And so that is where the local min will occur. We could also find the local min, so we could plug it in now. So we know that 1 squared plus 3 squared minus 2 times 1 minus 6 times 3 plus 14, that should be equal to the local min. Actually, in this case, it's also the absolute min, but that's just based on the type of surface we have. And if you do all that on a calculator, you get 4. But the question really said find all points where the local max or min occurs, and the local min, which we know, right, occurs at 1, 3. I guess we'll even put it like that, 1, 3, 4. All right, so this thing is one of those saddle surfaces, y squared minus x squared. And if we were asked to find a local max or min, you'll see there's a reason I'm putting it in quotes actually right now. So if you do your partials, f with respect to x is 2x, which we're going to set equal to 0 and get x is 0. And then we can do f with respect to y, and we would get 2y. And then I just realized that should be minus, sorry, but it's not going to change it because you just divide by -2. Then set that equal to 0, and then y equals 0. So it's saying that a critical point happens basically right here. But the issue is this point, is simultaneously like a minimum, like that, and it can also be a maximum, right? Go back down there. So this is actually an issue, and this is something that we actually have a way to deal with, but more formally, what we actually do in math is we sort of imagine like a little neighborhood, and the neighborhood around that point, if there's spots where it's simultaneously higher and lower than the quote-unquote local min or max, then we determine that there actually is none. So this is actually neither. And I'll define what this point is called on the next slide, actually, but there is, this thing actually has no local max or min. All right, and luckily there's a very formal way to figure out when this happens, and that is the second derivative test. So in Calc 1, your second derivative test basically just measures if something's concave up or down. And we check that if the second derivative is greater than 0, then it's a local minimum, because basically it's concave up. And if it's less than 0, then it's a local max, right, like this. And if it equals 0, then it's inconclusive. And that's honestly still kind of what we do, but the way that we have to measure it is a little bit weirder. So I talked briefly that the second, or the mixed partials, I should say, the xy and the yx one, that they measure sort of the twist in the surface. And we could talk about why that needs to be there, but it's basically just this is a more complicated second derivative test than this, but it's still doing the same thing. It's going to tell you, by taking into account the twist of the surface, and still also the concavity part, which is really the pure second partials, like the concavity in different directions, I should say. So if we take all that into account in a special way here, then we still are really doing the same thing. So what the formal second derivative test says is just that assume basically that your second partial of f are all continuous on some like disk, so that neighborhood I was talking about around the point, and suppose that f with respect to x is 0 and f with respect to y at that point is 0. So basically it's a critical point, right? Then there's this weird computation with the second derivatives, and there's luckily a way to remember what this thing is. They call it d. They're just defining it as d. But if this thing, this like subtraction of this weird product here, is greater than 0, and the second partial with respect to x is also greater than 0, then it's a local min. All right, and if that thing is greater than 0 and the second partial with respect to x is less than 0, then it's a max. If this thing is less than 0, though, then there's neither, and that neither case actually gets the name saddle point, and it really gets saddle point because of this classic example. So that thing looks like a saddle, and that's where you can get these weird spots that are neither maximums or minimums. So I want to go through an example and show you kind of how we do this. But before I do that, I want to make sure you kind of see that this is not some weird, messy thing that you have to remember. You kind of do need to remember these things. Mostly like greater than zero, local min. Which isn't too hard to remember, because if it's greater than 0, it's concave up, so it's a min, right? And if this is less than 0, right, then it's going to be a max. So it's not too hard to remember, but you just have to know that when this thing is less than 0, it's the saddle point, which is neither. And if it's greater than 0, then you're going to get an answer. But there is a way to remember this part. And that is this. All right, so the way to remember the second order derivative test, more specifically, really just remembering what D is, that thing. Good news is it's actually comes out of just a determinant, and we've seen determinants. We saw it, basically we saw one where A is like I hat, and then this is like J hat, and this is like K hat. And this is like our determinant of a 3x3 was 3x3 matrix was our cross product. And the this thing down here is a 2x2 matrix of the mixed partials. Okay. Well, not really mixed partial. I guess just all second order partials, basically. And determinants, like right now I'm teaching linear algebra, and in that class I talk a lot more about what a determinant really is. Very generally speaking, a determinant measures the scale factor change of a linear transformation, which probably means very little right now, and it shouldn't mean much to you. But it basically is a measurement of how something, very generally speaking, is how it's changing, sort of. And the derivatives in here, if you put all the second partial derivatives in and take the determinant of that matrix, you get this thing D. You would get, basically you just get this minus this. When we do cross product, that's how we do it. We like blank this out and we do this minus this. It's like these are little mini 2x2 determinants inside of a 3x3 determinant. You can do this for even 4x4s. Like you can blank out this, and then, do that first thing, which, typically what you're thinking of as I hat, doing that times the determinant of a 3x3. And then you can blank out this, and you get the determinant, or B times the determinant of this. And just remember that the signs always alternate, so you always have plus, minus, plus in the cross product. That also continues. You go plus, minus, you just keep going. So here we're doing plus, minus, is really what's going on. But, really it truly is like blank this out, blank this. So you're doing like f with respect to x twice, then times in a sense, 1x1 determinant, which is just like f y. And then you're minusing the next term. You're blanking out this guy and the row and column through there. And then you're multiplying by just a 1x1 determinant, which is really just, to do too many circles, f, y, x. But we're using the fact that the mixed partials are the same. So that's why we get this result. So don't need to really memorize this. You can just remember that it comes out of a determinant of a 2x2 matrix. A Hessian matrix, not that you need to know this either, but a Hessian matrix is a matrix filled with all the partial derivatives, like second order partials, basically. Maybe just to kind of show you guys really quick. So it's only, like Hessian matrices can only be square, and you can only take the determinant of a square matrix. This pattern that I'm talking about here with like a 4x4 or 3x3 or 2x2, that does not work, obviously, if it's not square. So just to kind of see what a 3x3 one looks like, you would basically have, I always just think about it this way, f x, f y, f z, f x, f y, f z, and like a quick way to check, to make sure that you're not missing any partials is to just do this kind of thing. I think I've got them all. And so this matrix right here is a 3x3 matrix. And if you needed to, technically you can do the second order derivative test for higher dimensional functions as well. And you would just need to use this matrix instead of this matrix. And so your determinant will just be a lot more terms going on. But it still scales perfectly nice with the theory behind the determinant of this. Now, I don't plan to do this with you because it's just a lot of work that's not too fun. But you do need to know how to do this one. So let's do one of those. All right. So we're going to find all local max and min values and saddle points of this weird function of two inputs. And the fact that we don't know what this thing looks like is why it will be nice to know how to do that second derivative test. Because if we didn't do that, basically we'd just be really, really hard to know what's a local max or min. You couldn't just use intuition like knowing that it's a paraboloid or something like that. So we got to find out critical points first. So let's do that. So we got to get f with respect to x, which is going to be 4x cubed minus 4y. Yep. And then we're going to set that equal to 0. We also need f with respect to y. So this is going to be 4y cubed minus 4x this time. We're going to set that equal to 0. So from here, this first one, this implies like you could divide out by 4 and then move the y. So y could equal x cubed. And so then I'm going to take this, I'm going to sub it into that second equation, right? So I've got basically x cubed in there. So 4 times y cubed. So I'm plugged in my my x cubed is y, and I'm going to cube it. And then I got minus 4x, and I'm setting that equal to 0. I'm also going to drop the 4s on this one, so x to the 9th now, right? Factor out an x. And then this tells me one root is 0, right? This thing is a difference of perfect squares, x to the 4th minus 1, x to the 4th plus 1. And this thing is also a difference of perfect squares. So x squared minus 1, x squared plus 1, and then we have x to the 4th plus 1. The question specified that we should only assume real values for x and y. This thing and this thing both only have imaginary roots, right? Like if you think about it, that one's really easy to draw. It just looks like that. And this is basically the same idea, honestly. It's just like it's a little flatter, right? Is actually what it looks like. but both of those are just shifted up one, and they don't cross the x-axis where we normally can see. So they have the imaginary roots. So basically, x equals plus or minus 1, and then also don't forget about that 0 over there. And that means, I'm going to actually kind of break this down right here. So I've got my critical points. If you go plug in x equals plus or minus 1 and 0, then like you plug it in like right here is what I'm saying, then you will be able to get the full, critical point in terms of like x and y. So plug in 0, right, you're going to get 0. And then plug in 1, you're going to get 1. And plug in -1, you're going to get -1. Okay. So now that is the critical points, and you've got to use the second derivative test to check what's happening basically at those points. So that's what I'm going to do on the second side of this, okay? I need my second partials, right? So f with respect to x twice is 12x squared. F with respect to xy is 4. Actually, no, it's -4. Sorry. Then f with respect to y twice is 12y squared. All right. And so if you set up your like 2x2 Hessian matrix, and you take the determinant, you should get 144 x squared y squared minus 16. Yeah. Now, you can go ahead and basically evaluate. So this will be kind of the end result here. So if you do 0, 0, we need to evaluate this d thing at that point, right? So if you plug in 0, 0, you get -16. So you can see that here d is less than 0, and that is our saddle case. Okay, so that's neither. And then if you plug in 1, 1, right, you get 144 minus 16, so d is greater than 0. And we also need to check this thing, right, the second derivative test. If you go back to it, you have to check the second partial with respect to x. And if it's greater than 0, it's kind of like this case, and it's min. If it's less than 0, it's like this case, and it's max. So if you do that at 1, 1, you'll notice that this thing is greater than 1, so we get a minimum. And last but not least, -1, -1. You're still going to get d greater than 0, like because it's squared in here. The negatives just don't matter, right? And then here, fxx is less than 0. Yeah. Nope, I looked at the wrong thing. It's definitely greater than 0. It's too much math on this page. I looked at this for a second, and I saw negative, and that sounded wrong in my head. This is what you should be looking at. So if you plug in -1 there, right, you just square it, it goes positive. So it's a min again. So 0, 0, saddle point, 1, 1, min, -1, -1, also a min. And I would recommend you actually go to like Math 3D or something and plug this in, and you can actually see it. You should be able to notice that really is what's happening. All right, just want to do one more example here. So just to show you, hopefully in BC you did some problems where you do these like optimization problems with like applications. And you can do that kind of stuff here. So it's got a rectangular box without a lid, is to be made out of 12 meters squared of cardboard. and I want to find the max volume of that box, okay? And so the function that I'm maximizing is just like x times y times z, right? And I say, hint, when computing your critical points in this problem, could x and y equal 0? So think about it. No. Because we're talking about dimensions of a rectangular box. So it doesn't make sense to have those be 0. So if that happens, something weird's going on, basically. All right. So we're making this out of 12 meters squared of cardboard. And so that's going to be this right here is another equation I can get, right? So I have the volume equation already. And then we know that if we multiply xy, like the base, and we add that to 2x, we'll do 2 zy, so the two ends in a sense, right? And then we add to that 2xz, which is the other two sides, right? Like this side and the side back there. All that needs to be 12, right? There's no top to it. And so you can solve this thing for z, and I'm going to trust that you can do that, and I'm just going to tell you should get this. And then we can substitute. Right? And then that thing is basically what I need to take my partials of, right? So for the sake of time, I'm going to write down what you get when you take your two partials. All right, so we're setting those both equal to 0. And so what this is saying, right, is that, if a fraction equals 0, then the numerators are the things that have to be 0. So these two numerators both basically need to equal 0, which is saying that, since this part and this part in here are the same, then this x squared and y squared need to be equal, right? We would need that y squared equals x squared, or just like y equals x, right? And if y equals x, then I can take something like what I have here, and I can plug in y equals x, and just turn it all into say, x's or something. So then that would simplify to 12 minus 3x squared, and that thing needs to be 0. And if you solve that out, you would get x equals plus or minus 2, but minus doesn't make sense because it's distances, so x is 2. And then since y and x have to be the same, also y has to be 2, right? And basically now we'll have it. So we can just do z equals 12 minus x times y, so 4, over 2 times y, which is 4, minus 2 times 2, which is, plus, which I just realized this should be plus, and this should be plus. There we go. That's what it should be. And then this should equal 1. And so if you do now the volume, right, equals x times y times z, then you would get just 1 times 2 times 2, or 4 meters cubed. So yeah, over here, if you solve this thing out for z, I just looked at it again, and I realized that that should be a plus in there, not a minus. So that changed that one. But anyways, sorry about that.